2 will be going over the Unit 5 problem set, which is basically the study guide for everything we've done so far in Unit 5. So I'm going to quickly go through this so you get an idea of what you're going to be looking at. Okay, let's get started. Number 1. Using principles of atomic theory, explain why C has a larger first ionization energy than B. So C is carbon and B is boron. Let's see. Where is boron? Okay, so here's how we start. Since carbon and boron are in the same period, they have the same amount of electron shells, meaning the electron shielding that protects the outer electrons from the full force of the nucleus for both of them are the same. But carbon has more protons than boron. This means that the force of attraction is stronger due to a larger amount of protons in the nucleus pulling on the electrons. Since the force of attraction or electronegativity is stronger, the ionization or the energy required to pull an electron apart from its atom needed for carbon is also larger than that of boron. Okay, number 2. Which element has a larger radius, F1 minus or Na1 plus? Na1 plus. Okay. So F1 minus and Na1 plus both have the same electron configuration, meaning that they have the same number of full energy levels. But since sodium has more protons than fluorine, we can use Coulomb's law of attraction to know that the attraction on the electrons will be stronger the force of attraction on the electrons will be stronger on Na cation than that of fluorine anion. With a stronger force of attraction and the electron shielding that keeps the outer shell electrons from the full force of the nucleus being the same, sodium will have a smaller radius, and therefore the element with a larger atomic radius would be fluorine. So put into the simplest terms, that is because fluorine has less protons pulling on the electrons than Na. Number 3, using principles of atomic theory, explain why the second ionization of energy for K is stronger than the second ionization of energy of Ca. Okay. The second ionization energy or the energy needed to remove the second electron from its atom is much stronger in potassium than that of calcium, because when removing the second electron of potassium, which only has one valence electron, we will need to jump a whole energy level that is closer to the nucleus. And after that, when an energy level becomes closer to the nucleus, the necessary energy will increase significantly. Calcium, on the other hand, does not have to jump in energy level when its second electron is removed, as it has two valence electrons. Therefore, when compared with calcium, the second ionization energy of potassium will be much higher. Alright, next, draw all possible Lewis structures for, okay, so first, let's count the number of valence electrons. We have 5 plus 6 times 2, which is 17, plus 1, 18 valence electrons, and N, O, O. I have 8 and 8, 17, 18. Alright, as you can see, the central atom doesn't have enough electrons, so we're going to have to add a double bond over here. Alright, now this way, everything has 8, and I'm going to put 1 minus, draw the opposite way. Oh, this is a single bond here. These single and double bond can switch places, so that'll become O double bond and O single bond. 1, 2, 3 minus. These are the two. These two will basically be resonance of each other. That's why I have to draw both of them. Okay, so now we're gonna do shapes, hybridization, and polar and nonpolar. Right. First, let's write sulfur hexafluoride, SF6. Sulfur has 6 plus 7 times 6 equals 48. And let's draw. We're gonna zoom in a little bit. S 1, 2, 3, 4, 5, 6, and if each of them have 8, 6 times 8 is 48. So each of them can have 8, 2, 3, 4, 5, 6. There we go. And now the S will be an expanded octet. So the shape will be 6 bonding pairs. 6 bonding pairs is octahedral. Alright, and then the hybridization, you have 6 things around it. And then 6 things around the central atom means sp3d2. Now, is it polar or nonpolar? As you can see, there's no lone pairs. There's no dipoles in lone pairs, and also all the elements around the sulfur is exactly the same. So this will be nonpolar. Next, boron tribromide, B and Br3. B has 3. Br has 7 times 3, 24. So B and 3 BRs. Alright, if all of these are filled, we'll have 24 electrons, but the central boron will not fill the octet role. So we're going to have to add a double bond in one of these. One, two. Actually, I'll draw it a different way so you guys can see how you can use both ways. But on the exam, try to stick with one way to draw them. Either use lines or dots. Right there. Now this one has 3 bonding pairs and no lone pairs in the middle. So 3 bonding pair is trigonal planar. And now since it has three things around it, it's going to be sp2. And all the Br are the same and there's no dipoles, so this will be nonpolar as well. Next one, phosphide anion. Phosphide is PO3 3 minus. So PO3 3 minus will be P in the middle, 1, 2, 3. If you add up everything together, P has how many valence electrons? P has 5. 5 plus 6 times 3 plus 3. That should be equal to 26. 1, 2, 3. This will add it to 22. So we're going to have to add a lone pair over here. Alright, so after we do all of this, we still have an extra 2 electrons remaining. So we have to add that to the lone pair in the center to make the center atom 8. And now, if we look at this one, there's 3 times 8, 24. This one has 24 valence electrons. And after I draw all of these, if I put 8 on each of the outer ones, there will be a total of 24, yet the central one doesn't have enough. So when you don't have enough electrons, you add double bonds. But over here, we have 2 extra. After I filled everything else on the outside already, I will have 2 extra electrons with a 26. And that's when I add lone pairs. So now we have 3 bonding pairs. 3 bonding pairs and 1 lone pair. Alright, so 3 bonding pairs and 1 lone pair is trigonal pyramidal. And how many things is around it? We have 1 lone pair and 3 bonding pairs. So 4 things around it will be sp3. And since it has a dipole, aka lone pair, since it has a lone pair, although all the outer atoms are the same, with that dipole do not canceling out, we have this as a polar. And the final one is TeCl4 2 minus. Te has 6, Cl has 7 times 4 plus 2 plus that, and that is equal to 36. Alright, so 36, we're going to draw it on the side over here, Te, Cl, 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 Cl. If all of these has 8, that will be 32. So that means we have extra electrons, 4 extra electrons. So we're going to have to add them as lone pairs. 1, 2, 3, 4, 5, 6. Alright, now this one will have 4 bonding pairs and 2 lone pairs. That is 4 bonding pairs and 2 lone pairs. Square planar. And now how many things is around it? We have 4 bonding pairs around the Te and 2 lone pairs. So that is a total of 6 things around the central atom. 6 things is sp3d2. And the polar, you have 2 lone pairs, not 3. So dipoles do not cancel out again. And since dipoles do not cancel out, this will again be polar. Okay, so again, if all these outer ones are the same, which in this case it does, it should be nonpolar. But since there's a lone pair, since there's 2 lone pairs in here, dipoles do not cancel out, which makes it polar. If this central atom has 3 lone pairs, then you will say all the dipoles do cancel out, and then that will be nonpolar again. So right now it's polar due to the dipoles it has in the middle. Okay, so next we have to find pi and sigma bonds. Alright, so pi bonds only occur in type 2 and type 3 bonds, while sigma bonds are in everything. So that's some good to know information. Let's start going. Sigma bonds. Okay, so for this one you have to be a little careful because although it looks like there's 1, 2, 3, 4, 5, no, 1, 2, 3, 4, 5, 6, 7. Although it looks like there's 7 sigma bonds, but we gotta take in account of everything else. So we're gonna split this apart, C and H. Alright, see what I'm doing here? CH3, there's bonding itself between these C and H's too. That is not shown, but you have to take those into account. So C, which is bonded to 2 H's, bonded to C, which is bonded to 1 H, triple bonded to a C, which is bonded to an H, bonded to another C, no, double bond, sorry. Double bond to a C, which is bonded to another C and an H, and a triple bond. Oops, drew too much. Alright, so we have this one, which matches this one, which matches this one, which matches this one, which matches this, and bonded to another C. Alright, I know. Gotta be careful when we're drawing these. Alright, so this will be bonded to a C, which triple bonds to another C, which bonds to another C, which bonds to 2 H's, and that will bond to C with 3 H's. Okay, now we're done, and now we can start counting. So every single bond has 1 sigma bond, and double bonds has 1 pi bond, and triple bonds has 2 pi bonds. So first count the number of bonds: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. There's 19 bonds, therefore 19 sigma bonds. Now pi bonds only occur in double and triple bonds. So there's 1 double and 1 triple bond. Double bonds contain 1 pi bond. This one, triple bond, contains 2 pi bonds. So you add them together, and that is equal to 3 pi bonds and 19 sigma bonds. Number 18. In which of the following molecules would you expect the central atom to employ sp3d2? So we need to find one that has 6 things around it. Okay, so let's first with phosphorus, P, pentafluoride, F5. Alright, so as you can see already straight away, there's only 5 things around it. So this is not likely. Although we didn't take account into lone pairs, we can see that this is not likely. Let's keep moving on. Carbon dioxide, you don't need to think about it. It's C and 2 O's next to it. There's no way there's 6 things around it. So B is obviously out. Bromine pentafluoride, BrP5. Again, this one only has 5 things around it. Although we didn't take into account of the lone pairs, we can say that this is not likely. But if you look at silicon dioxide, SiOO, something like this, we don't even care how much lone pairs it has, it will never have 6 things around the center atom. So now we have to debate between A and C, and we're going to see which one of these has lone pairs on the central element. So let's zoom in. Alright, P has 5 plus 7 times 7. Now this is 40. So let's draw P. And 1, 2, 3, 4, 5. 5 F's. If all 5 of these F's are filled, they will have a total of 40. So this one has no lone pairs. Now our only answer available is D. And let's double check that. Alright, so since if all these F were filled, if I were to draw off these, you'll have 40. And 40 matches this, so there will be no lone pairs needed in the middle, so that would not be the right answer. Let's draw BrP5 real quick. P has 5. 5 times 5 plus Br, which is 7. Okay. 32. Alright. Now 32, let's draw Br. Oh shoot, bromine pentafluoride, not P. Whoops. Okay, so we're gonna change this a little bit. Okay, so it's Br, so Br is 7 plus 7 times 5. Okay, so basically 5 times 8. No, 7 times 6. 42. So this one have 42. Okay, now as we can see, it has 2 more electrons, so we already know it has a lone pair, so we already know this is the correct answer. But let me just show it real quick. So we'll have Br in the middle, 1, 2, 3, 4, 5, F, 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 F. Now if we were to fill all of these F, we'll have 40 again. See, 5 times 8 is 40. Alright, now this one has 8, 8, 8, 8, 8, 40. but we have 42. That means we'll have two lone pairs. No, we have two extra electrons, and that can only go to the lone pairs. This means the central BR will have 1, 2, 3, 4, 5, 6. 6 things around it. So this will have the hybridization of sp3d2. So our correct answer here is C, because it has 5 bonds around it plus a lone pair, which makes it 6. Now, which of these is not polar? So nonpolar. The rule for nonpolar is that if it's symmetrical, no, if it doesn't have a central atom, it has to be symmetrical. If it does have a central atom, it has to be, everything around it has to be equal without any lone pairs. So CO is not symmetrical whatsoever, so CO is out. And we can take HBr, is not symmetrical, so this is out. Now we're left with our CH3 3Cl. This is already out, obviously. So now we're left with NH3 and Ge4. Let's work with NH3. So we have N in the middle, N in the middle, 3 H's around it. Alright, now in order to fill the octet rule, the N has to have a lone pairs. Right, let's double check. 3 plus N, which is 5, is 8. So 2, 4, 6, 8. So this has to have a lone pair. And although all the hydrogen around it is the same, due to that lone pair, it makes it polar. So now let's see if this has a lone pair. Now GF4 is G in the middle, 1, 2, 3, 4, F, 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 F. If all of these F were filled, like what we have over here, it'll be 8 times 4, which is 40. So let's just check if GF will have 40. So first we have 7 times 4. No, 4 times 8, 32, my bad. So this will be 32. So first we have 4 times 7 plus GE, which is 4, which equals 32. And now again, 4 times 8 over here is 32. Since if this filled, this will have 8, this will have 8, this will have 8, and this will have 8. So 32 matches, so there will be no lone pair required. So our answer is E, GeF4. And now what is the formal charge assigned to the carbonate atom in carbonate ion? Okay, so we're gonna have to find the formal charge in carbonate ion. Carbonate is CO3 2 minus. Alright, so CO3 2 minus. Let's first draw one. CO3. So C in the middle and 3 O's around it. CO3 2 minus. Let's see. O has 6. 6 times 3 plus carbon, which has 4. 22. Plus 2 more, 24. No, 23. Alright, 24. Perfect. So now let's draw. If all of these have 8, then that would be 24 already. But our central one doesn't even have, doesn't fill octet rule. So one of these has to be a double bond. Alright, now this matches this. Now we should see if it matches formal charge. So let's see the C. The C has a valence electron of 4. Subtracted by the number of things around it. We have 1, 2, 3. We have 1, 2, 3, 4. 4 things around it. So that equals 0. Now the double bond O has 6 valence electrons minus 1, 2, 3, 4. 4 things around it, which equals positive 2. And then finally our single bond O, which has 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7. 7 things around it, which equals negative 1. Oh, my bad. Alright, so here's the thing you have to be careful of. Alright, each of these lines is actually 2. Alright, I thought for my own thing. So 2. Each of these lines actually means 2. So technically, if it's not a bond, it has to be counted as 2, which is why this has to be 6, which turns this into 0. Alright, again. So I have 1, 2. Each of these count as 1. 3, 4, 5, 6. Now note, this does not count towards the hybridization. Hybridization only bonding and lone pairs count. But over here, each individual electron counts as well. So if you're drawing lines, you gotta be really careful because again, you couldn't make the same mistake I made. So let's not draw lines over here, and let's simply do it as this: 1, 2, 3, 4, 5, 6. So 6 minus 6 is 0. Let's not do lines over here. 1, 2, 3, 4, 5, 6. So I have 1, 2, 3, 4, 5, 6 plus this one 7. 6 minus 7, -1. So how much C do we have? We have 1 C plus how much double bonded O do we have? We have 1 double bonded O, which is also 0 from here and here. So this is a double bond O, plus 2 -1s from the single bonded O's. So 0 plus 0 plus 0, 0 plus 0 plus -1 plus -1 equal to -2. And this matches our charge over here, which is now that we know that this is the formal charge. And we're supposed to draw the different types of it. So we can do that real quick. 1, 2, 3, 1, 2, oh, single bond, double bond O. So 1, 2, 1, 2, and alright, that's another one, and a third one would be this. Double bond over here, and this is our 3 types that will all fit as the formal charge. Now moving on to number 24, it said if they're true or false, and if false, explain why. Alright, first one. The central atom of all stable molecules have an octet of electrons. Octet has 5. So octet have 8 electrons, but that is not true because we learned about expanded octets. So false. There can be an expanded octet. For example, an element that has 5 bonding pairs. We saw many examples up there, like P3, yeah, PF5, etc. All of these has an expanded octet. So this is 100% false. Next one, the bonding between 2 carbon atoms with a triple bond is shorter than a single bond between 2 carbon atoms. Right? So a triple bond means a stronger bond. A single bond means a weaker bond. Obviously, the stronger bond will have the 2 atoms closer together than the weaker bond. So this is true. Right, number 26. In general, electronegativity values of elements increase toward the top and right corner. This is also true because, as we learned, F fluorine has the highest electronegativity, and it decreases as it goes down and increases as it goes right, which is basically another way of reformatting what this says. F has the highest electronegativity value, and this matches it. Right, finally, a binary compound consisting of one element having low ionization energy and the second element having high ionization is likely to possess covalent compounds. Now this one is false. And why? Because if there is a high difference in electronegativity, because one of them has low, if there's a high difference in electronegativity, then it's more likely to possess ionic bond, since 0 to 0.3 is equal to covalent, is nonpolar covalent, and 0.3 to 1.7 is polar covalent. And now if there's a high difference, which is the situation we're having over here, since one of them has high electronegativity value, then most likely, not saying you 100% will, most likely you'll have ionic, because 1.7 plus is ionic bonding. Alright, explain the magnitude of these lattice energies and size of their charge. Alright, so this one we'll have to explain about lattice energy. Lattice energy is the energy required to turn a compound from gas form to solid. The rule for lattice energy is that as charge increase, lattice energy increase. As distance increase, lattice energy decrease. In this chart, we can tell that all of the charges are the same, which is 1 minus and 1 plus from the K. Alright, and it's obviously shown right here. So as they're in the same group, then we'll have to take a look at the atomic radius. Iodine has the largest atomic radius, as it has 5 electron shells, and also therefore it will have the weakest lattice energy. Br has 4 electron shells, Cl has 3, and F only has 2. That's why it goes from 682 of Br and gets bigger and bigger until it reaches fluoride, which has 821. And hopefully this makes sense. So lattice energy decreases as distance increases. I has the biggest distance, so therefore the smallest lattice energy. F has the smallest distance, and therefore the highest lattice energy. Alright, now next one. Which of these following crystals, ionic crystals, do you predict have the highest lattice energy? Again, more charge equals more ionic energy, right? So first let's find that. No, more charge equals more lattice energy. Li only has 1 plus, so does Cl. Cl has 1 minus. So 1 plus 1 minus, 1 plus 1 minus. Ca has 2 plus, so this is 2 plus 2 minus. SRO is also 2 plus 2 minus. And KCl 1 plus 1 minus. Right. So all of these only have the charge of 1, while these two have the charge of 2. So the largest energy is obviously in between one of these. Now, since both of these has oxygen, we're going to see which of these has a smaller atomic radius. Since smaller radius equals larger ionization energy. So Ca is number 20, while Sr is number 38. That means Sr has a whole extra electron shell, meaning more electron shielding, which means bigger radius. So bigger radius means smaller lattice energy. So this one has a smaller lattice energy, and the largest lattice energy will therefore be CaO. Now, when covalent compound is formed between two different elements, when a covalent compound forms, the bond is obviously not ionic, since I told you it's covalent. Both atoms attain an inert gas configuration. Not sure what that is. The electrons of the bond are shared equally. No, it's two different. One of them is a metallic. It doesn't have to be. The electrons of the bond spend more time in the vicinity of the more electronegative element. Alright, this is the only one that makes sense, because in the more electronegative element, it wants more electrons. So the electrons in the bond will be more in the more electronegative element. Since it's more electronegative, it pulls more on these electrons. So E. Now calculate the bond type. Order them from most covalent to least covalent, and this one you're gonna need to have the chart with you, but we can do some predictions over here. Alright. F is the highest electronegativity value. H is a little bit lower, so H minus F should 100% be equal to ionic, since F is so big. Now, I'm just going to give you the rest of the numbers here and let you figure it out. 3 minus 0.9 equals 2.1, which is ionic. F is 4 minus H, which is 2.1, is 1.9 ionic. 2.1 minus 1 is equal to 1.1 covalent. 3.5 minus 0.8 is equal to 2.7 ionic. And Cl is 2 minus 2.1, which equals 0.9 covalent. Alright, now these numbers is from the electronegativity chart that I showed a couple videos ago, and I do not have that with me, and I'm pretty sure you will not have that on the test with you. So on the test, you're going to have to infer with your knowledge about electronegativity. F has the highest, top right corner is more electronegative, and everything else is less electronegative. You need to have to use that knowledge to predict. right? It will not make it really close like we have over here 2.1, 2.7, both ionic, and without the numbers you won't know. So now let's order from most covalent, which means least number, will be E, then C, and then B, and then A, finally D. Alright, more covalent equal less number, more ionic equal a higher number. Which of the following contain both ionic and covalent bonds? Okay, so ionic bond and covalent bond. NaOH is covalent. No, NaOH is ionic. H2O are both gases, so that's covalent. So we define one that has gases and nonmetal. Sorry, Si is a nonmetal, O2 is also nonmetal. So all of these are cancelled out. That leaves us only with C. See, there's metals and nonmetals. Oh no, there's only nonmetals, but Cl is an ion. Cl is an ion, and in order to bond with that, you're gonna have to have Cl. You're gonna have to have an ionic, and the other C, which bond with the Hs, will be all covalent. So this one will have both covalent and ionic. So now we draw isomers for C6H12. Alright, so first let's start with the most common type. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Alright. So each of these two will have two H's. 2, 1, 2, 1, 2, 1, 2, 1, 2. And now we're gonna need some double bonds. No, we don't. All of these have 8, I think. Yeah, all of these bonds have 8. Okay, now let's draw another way. What is another way that you can draw? You're gonna have to use your brain for a little bit. So we could draw like this: 1, 2, 3, 4, 5, 6, right? 1, 2, 3, 4, 5, 6, and each of these will have two H's next to it. Okay, so now that makes sense. Alright, as you can see, these H bonds and C bonds were physically broken apart in order to form this one. Now we have to think of one more. Okay, so an easy one would be breaking this one apart and shoving it over here, right? Although it's only breaking one apart, but it's still an isomer. So let's draw that. We have H, C, 1, 2, 1, 3, 4, 5. Alright, so basically what I did was break this one, put this one over here, and break this one, bring it over here, so that, alright, the bonds are broken, right? And that's the definition of an isomer, so this will work. Alright, now we draw 3 already. For the following, determine the orientation of the dipole moment, if any, by drawing the dipole. Is the molecule polar or nonpolar? Okay, so first, let's do HI. From the look of it, we already know it's going to be polar, 100%. Now this is 8 valence electrons, so this one's already full since H only need 2. 1, 2, 3, 4, 3, 4, 5, 6, 7, 8. Is there a dipole moment? 100%. Since this is polar, we know this is polar, and we're gonna draw this by showing this. The arrow is gonna point toward the more electronegative element. So N2. Alright, so far from the look of it, it's nonpolar. So let's double check that by drawing N. Alright, so N has 5, 10. So if we do 2, 4, 6, 8, 9, 10, this won't be enough. So we're gonna have to make a double bond over here. 2, 4, 6, 8. Yeah, perfect. Alright, since both of these elements are equal and the number of electrons they have is equal, there will not be any arrows anywhere, so this is nonpolar. Finally, CClF. Alright, we have C over here, Cl on top, and F on the bottom. Let's do it that way. Alright, again, so first let's see if there's C has 4, Cl has 7 times 2, 14, F has 14, so 28, 32. 4 times 8 is 32, so there will be no dipoles, but all of these will be filled real quick. From the look of it, we know this is polar since all the atoms around the carbon is not equal. But we have to draw the dipole moment. So we're gonna see if F is the most electronegative. So no doubt there will be two arrows pointing toward F. And on the other side, you're gonna add a plus, just so you know that this side is more positive due to the fluorine. And Cl is right below fluorine, whereas carbon is couple ones next to it. So we can tell that Cl also has a high electronegativity. So you're also going to draw the arrows and state that this is polar. Okay. Types of bonding. When difference in electronegativity is 2.0, or this is ionic without a doubt. Highest electroconductivity for copper. Copper is a metal, metallic bond. When electron pair is shared unequally between an atom, what type of bond? So it's unevenly, but it's shared, so it will be nonpolar covalent. Now, what type of bond will be predicting sodium oxide? So NaO. Right, O has a very high one, whereas Na has very low since it's all the way to the left. So it's going to be high minus low. So we can predict that this will be ionic since O is very high, Na is very low. A high number minus a lower number is most likely ionic. What type of body would you expect to produce hydrogen selenide gas? So H is 2.1. You should memorize that. And now S is right next to H. S is right next to Cl. So you can tell that S is also pretty big. So now let's count. So S will have 6, 7, 8. So 8 valence electrons, 1, 2, 3, 4, 5, 6, 7, 8. And now due to these lone pairs, this will make it polar. So polar covalent. Since it's not too, the numbers are not too far away to become ionic yet, but this S has lone pairs, and this makes it polar. And now finally, all we have to do is now draw different shapes and state if it's polar or non-polar. So first things first, we'll have iodine trichloride. So this is ICl3. I is 7, Cl is also 7, so 7 times 4, 28. Alright, so I, Cl, Cl, Cl. Whoops. Alright, if I fill off this will only have 24. So 25, 26, 27, 28. I need 4 more. 1, 2, 3, 4. I have to draw them here. And this will be polar due to dipoles not canceling out. So 3 bonding pairs and 2 lone pairs. 3 bonding pairs and 2 lone pairs is T shape. Next, phosphorus P pentacl5. P has 5. 5 plus 7 times 5, 40. So P, 1, 2, 3, 4, 5, Cl, 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 Cl. If each of these has 8, it'll become 40 exactly. So that's great. This will be nonpolar since there's no dipoles, and this has 5 bonding pairs. 5 bonding pairs make trigonal bipyramidal. Alright, I3, 1 minus. So 7 times 3, 21, plus 1, 22. Alright, and I, well, 1, 2, 3, 4, 5, 6, plus 8, and 8 over here. 20. This will have 18 plus 6, perfect. Alright, let me draw this better. So 22, and this will be, frankly, nonpolar since all the dipoles in this one cancel out. So 3 bonding pairs and 2 bonding pairs and 3 lone pairs make it linear. And now pH3, P in the middle, 1, 2, 3, H. Let's see, H each has 3 plus P, which has 5, 8, which makes 8, which means there will be a dipole over here to make it 8. P. Alright, let me see, it has to be dipole here, and due to that dipole is polar, and 3 bonding pair plus 1 lone pair is trigonal bi. Nope, I lied. Eraser. Trigonal pyramidal. No. 3 more. Sulfur tetrafluoride. So SF tetra 4. No, fluoride, yes, 4. So let's see what we have over here. F has, we've drawn this before, I swear. F has 7 times 4 plus S is a 6. Now that is equal to 34. 34, we're gonna have S in the middle and 1, 2, 3, 4, 4 F's around it. And now this will have a dipole since there's only 32 around it. So this will have a dipole, and dipole makes it polar. So 4 bonding pairs plus 1 lone pair. 4 bonding pairs and 1 lone pair makes it seesaw. Alright, now BeCl2. Be, which has 2, Cl, which has 7 times 2, 14, 16. Now BeCl, Cl. So if each of these has 8, it will be 16. Yet that wouldn't work since the center atom won't fulfill the octet rule. So our best way is to draw 2 double bonds, and that makes it 16. Now both elements around it is the same, and there's no lone pairs, so this is nonpolar, and 2 bonding pairs makes this linear. SnCl6 2 minus. So 4 plus 7 times 6 plus 2, that is 48. Now SN will go in the middle with 6 Cl's around it. Alright, now 8 times 6 is equal to 48, so that we know all these Cl's will be filled, and that basically finishes the job for us. Alright, now if we add all of these together, it's 48, and 48 matches to 48, so no lone pairs in the middle. Every single atom around it is all Cl, so this makes this nonpolar, and this will have 6 bonding pairs. 6 bonding pairs is octahedral, and that's it. That's it for the problem set and study guide. If you have any questions or if you need further explanation on one of them, leave them in the comments and I'll try to help you. Thank you for watching.